about the natural exponential function. Okay, now what I'm going to kind of get into this, what I'm going to do is I'm going to go about it this way. Okay, imagine that we have $1 and we've invest. So this is so this would be, according to this formula here, P would be 1 and 100% interest. So that means R would be 1 and 1 year. So that would be T1. T would be 1. Okay, and what we're going to do is increase the number of compoundings n per year. Okay, so essentially, here's what we have, and we're going to see what happens to the amount when we do that. When we keep on increasing the number of compoundings per year. Okay, so P is 1, and then we have 1 plus, and R is 1, and N we're going to be leaving that as like a constant, and then raising it to the N, and T is 1, so that's just raised to the N. Okay, so really, the amount that you're going to get is 1 plus 1 over N to the nth power. Okay, now, what I'm gonna do this in Excel. I'm going to show you in Excel, and we'll start with n equals 1, and then we'll go n equals, I don't know, 12. So this would be annually, and this would be monthly. Then we can do 365, we can do daily, and then we'll go up from there and see what happens, okay? See what happens, okay? So let's go, here's the formula right here. So let's go over to Excel. And I'm going to have, in the first column, I'm going to put N, and I'm going to put in the amount right there, okay? So I said annually, monthly, daily. Okay, those are the first values. Okay, now here, I put in the formula, which is going to be 1 plus 1 over, and then here I'm going to put A2 to the A2. Okay. Okay, so 100% interest, that's exactly what you expect. With 100% interest, you're going to get $1 doubles to $2 with 100% interest. Now, if you compound it monthly, you get $2.61. Okay, and if you compound it daily, it's $2.71 is what you end up with. Okay, now we can say let's do it hourly. So this would be 365 times, because there's 24 hours a day, so every hour we compound it, and that's how much you would get. And if you said, okay, let's do it per second, so equals 365 times 24 hours, 60 minutes in an hour, and 60 seconds in a minute. Okay, and so that would be, okay, so there's this many seconds in a year, and then this would be 2.718281. So it'd be $2.72. Okay, and then, you know, we can like make these numbers really big. Like, let's say we just put a 1 with a bunch of zeros behind it, really big, and even bigger. It might crash the, it might cause some weird things. Okay, this is weird because this is not right. Okay, this didn't work. So beyond that, we're starting to give us weird values that don't make any sense. So we're just going to cut that off right there. It turns out that this pretty much is this right here is pretty much the limiting value. This is out to quite a few decimal places. So so if you increase it, you're going to go towards this value here, 2.71828. Okay. Let's go back to the other document. And so basically what happens is it goes to about 2.7181828. This is the limiting value. And this number here, so this number can go out many places. And if you have very good computing, you can calculate this out to lots of decimal places. And this is to 5 decimal places. And this number is the limiting value is known as the number E. E. And here it is right here. This right here, where you take e to the x, where this number e this limiting value is called the natural exponential function. The number e is approximately this, round to 5 decimal places, 2.71828 is what it is approximately. Okay, so that's kind of introducing the number e. So it's the natural, and we're talking about exponential functions. This is the natural one. Just because, look, it naturally occurred here. We weren't just making this number up. You know, we were taking this, we were letting n get larger and larger and larger, and it converges to this e. Okay. It also appears in other places as well. Okay, but it's important for exponential functions. Okay, now, so here's a few values that we want to calculate. So h of 1/2. So h of x is e to the negative 2x. So h of 1/2 would be e to the negative 2 times 1/2. So that would be e to the negative 1. Okay, and we're going to evaluate that in a minute. H of 1.5, that would be e to the negative 2 times 1.5. So that would be e to the negative, what's 2 times 1.5 is 3. E to the negative 3. And then h of negative 1, so that would be e to the negative 2 times negative 1. That would be e to the positive 2. And h of negative pi, that would be e to the negative 2 times negative pi. That would be e to the 2 pi. Okay, so I'm going to show you how to. You can also you can use Excel for this, but you can also use GeoGebra. Let's do this, calculate these in GeoGebra this time. So let's switch over to GeoGebra. Okay, and I'm going to start the calculator. And it knows about the number e. So if you just type a little e and then you put a, there's the approximation for it right there, right as you type it in. If you raise it to the -1 power, then you're going to get, this is 0.3678, but you round that up to 3.368 because they want 3 decimal places. And then the next one was e to the negative 3. Oops. And there's that one. So that's 0.0497, but round to 3 decimal places is 0.05. And then the next one is e to the 2. And then the next one is e to the 2 pi. For pi, you can type a pi, and that changes to the symbol pi. So pi does that. So there's one thing that you got to be really careful about. Let me show you something. If I do another one of these, let's say e to the 5, okay? And then, I do one more, and then I do something else, okay? And then now let's suppose that I go back and I put, let me put e squared in again. E squared again. Okay, so now here, this e squared is like this weird number, and this e squared is that one. And we know this one's the correct one, but this is off. This is like a weird thing about GeoGebra. I'm just warning you right here. The reason is because this right here, when we put, it's using these letters here, A, B, C, D, and here it reassigned the value of E to this value here. And then, so then for this one, it's using this value for your E instead of the correct value. Okay, so I just wanted to point that out. That could be a possible thing that happens. Okay, so let's go back here to the PDF reader and put these values in. Okay, so that one was rounding to 3 decimal places. It was 0.368. That one was 0.05, rounding to 3 decimal places, and that one was 7.389, and that one was 535.492. Okay, and so those are the answers for that one. Let's move on to the next exercise. You can also use a calculator for these. Your calculator has the E in there, or E to the X button, and that's perfectly fine. Okay, now graphing the function. E to the X is going to be just like the other exponential function. It's going to be between the 3 to the X and 2 to the X, because E is like 2.7 something. So here, this is E to the negative X minus 1. Okay, this negative is inside. So it'll be a reflect. Oh dear. Okay, I hit the wrong spot here. Oh, hold on a second. Oh, come on. Okay. Okay, start again. Okay, so this is, okay, so this is inside. So that will be reflect through the y-axis. So it'll be a horizontal reflection through the y-axis, okay? And then this part right here is outside. So that will be a shift down by 1. Okay. So it's going to be this one right here. So you can see that it's been flipped through the, so this one right here has been flipped through the, actually it's been raised up by 1 though. This is flipped through the, so this is flipped through the, reflected through the y-axis and then shifted down by 1. This one's been shifted through the y-axis, but then shifted up by 1 instead. And this problem is also asking you for the domain and range. Okay, domain will be from negative infinity to infinity, and the range will be from negative 1 to infinity, not including negative 1 though, because it's been shifted down by 1. And then the exponential functions, just the standard ones, you know, without any shifts or translations or anything, they have the y-axis, the x-axis is x, or y equals 0 is the asymptote. So y equals negative 1 is the asymptote. Okay, so there's those answers there. Okay, let's go to the next one. Oh, more of the same. Okay, here, this is y equals e to the x minus 1 plus 2. Okay, so this one is inside. and so that will be shift right by 1, and this is outside, so that will be shifted up by 2, because it's +2 up. -1 means shift to the right when it's inside. Okay, so it's going to be the same shape like this, but it will be shifted up and to the right by 1. So let's see here. It looks like this is the only one that it can be. And the domain will be negative infinity to infinity, and the range will be 2 to infinity, because it's been shifted up by 2. And the asymptote will be y equals 2. Okay. That's second number 5. Animal populations are not capable of unrestricted growth because of limited habitat and food supplies. Under such conditions, the population follows a logistic growth model. Here it is right here, where C, D, and K are positive constants. For a certain fish population in a small pond, D is 1,000, K is 9, C is 0.2, and T is measured in years. So let's go ahead and plug all those values in. So D is up here in the numerator, that's 1,000, so that's 1,000 right there. And then in the denominator is 1, K is 9, so we'll put a 9 right there. And then e to the negative CT, so and here C is 0.2, so that's negative 0.2 T, and T is in years. Okay, great. So the questions are, how many fish were originally put in the pond? So this is when T is 0. What do we have when T is 0? Now for this one, what you can do is just plug a 0 in here. That's not too hard to plug in. It's also written as P of 0. You plug a 0 in here, plug a 0 in here. And that'll be e to the 0. And e to the 0 is 1. Okay, so you're going to get 1,000 over 10, which is 100. Answer to that's going to be 100 fish. Okay, now this one, here, in this first one, it finds the population for 10, 20, and 30 years. So you want T to be 10 here, you want T to be 20 here, and you want T to be 30 here. 10, 20, and 30. And then also for large values, what happens is T gets really, really large. So let's use Excel for this one because they're putting in a whole bunch of different values. So I'm going to put this formula into Excel. It's 1,000 over 1 plus 9 times e to the negative 0.2 t. Okay, so for this part, we're going to use Excel. And one thing to know about Excel is e to the x is exp of x, okay? So the e to the x would be, exp is the Excel notation for that. Exp will be the e, okay? That's in Excel. So this is all how to use Excel, basically. Okay, so let's go to Excel then. Okay, so I'm going to do it over here, and I'll save this and put it up on Canvas. I'll save this document and put it up on Canvas. Okay, so here we have time, and then here we have population. Okay, and we're going to put the 0 in just for a check. And they wanted those values initially. We'll put some more values in. We'll put some higher numbers in. And it was, remember, it was 1,000 divided by, and you got to use parentheses, 1 plus 9. And you got to use the times button. You can't just like leave no space in there. And here's where I said it's e to the negative 0.2t. So you put exp, and then in parentheses, you put negative 0.2 times. And then for t, you're going to put A11. Okay, that's going to give us the cell with the 0 in it, and then we close it off with parentheses like that. Okay, and that's 100 is the answer that we got for the first part, for part A, was 100, when t, and by plugging in t equals 0. Okay, and then here are the other values. So we want to round it to the nearest whole number, just because it's kind of weird to say, oh, there were 450.85 fish. You know, people would be like, that doesn't make any sense. I mean, maybe it does make sense, but, you know, people don't really think that way. So that would round, so the first one would round to 451. This would round to 858. This would round to 978. Okay, so we can go ahead and, let's go ahead and put those values in to the other document. So this one was 451. This one was 858. And this one is 978. Okay, now this one, this part right here, we're also going to use Excel as well for that one. Evaluate for large values of t. And what value does the population approach as t goes to infinity? So let's go back over to Excel. And we'll drag this down. It'll give us an error, but that's okay. We'll put larger values in. So let's say we go, let's just say we go 100 years. Okay, then it's 999.99 fish. That's approximately 1,000. If say we go 200 years, then that's 1,000. And if we go 300 years, if we go lots of years, that's 1,000. If you can go even more years, like more years than the history of the Earth, that's still 1,000. So the limiting value as you get bigger and bigger is just going to be 1,000. Okay. So let's go back over to the document, and that's the answer to that part is just going to be 1,000. And so here you're increasing like this. So 451, 5, and then 20 gives you there, and then the limiting value is 1,000. So yeah, this works out okay. Okay, let's look at number 6. In the formula for continuously compound interest, the letters P, R, and T stand for. Okay, let me explain this. Number 6. Okay, so if you go back to, we talked about this a little bit at the beginning on the first page. If you put all this other stuff in, this right here, this formula here, as n gets larger and larger, this converges to, let me just set here. So as n gets larger and larger, that means n is getting larger and larger and it's going to infinity, then this right here, 1 plus r over n to the nt, that's the formula for compound interest. That's going to go to p e to the rt. So this part just goes to e to the rt. And that's how you get that formula. So this is similar to the other one. So P is the principal. So P is the principal. R is the interest rate per year. And this one, T is the, no, T is the number of years. A of T is the amount after T years. Right there. And this is called continuously compounded interest. Okay, continuously. This is continuously. So this one is n compoundings per year. This one is continuously compounded. Okay, so if $100 is invested at an interest rate of 4% compounded continuously, then the amount after 2 years is blank. Okay, so this is telling you, let's see here. So 100 is going to be the principal, and 4%, that means that R will be 0.04, and 2 years, that means T is 2. So there's the formula. Just plug everything in. P is 100. E is itself. R and T. R is 0.04. T is 2. So that's 100 times e to the 0.08. Okay, and let's go back to GeoGebra. And remember, I messed up the GeoGebra, so let's, if it'll let me. Okay, well, let's just close this window. Okay, let's just close that GeoGebra window, leave it, and we'll open a new one, because that one was messed up. E no longer is the correct value. Okay, so we'll just put in 100 times 8 times e to the 0.08. Okay, so that's $108.33. We'll go put that in there. And we'll cite the source. That goes $108.33. And this is from GeoGebra. Okay, great. Let's look at the next problem. An investment is $1,000 is deposited into an account in which interest is compounded continuously. Complete the table. Oh, and T is 3 years. Okay, so that means that P is 3,000. And T is 3. Okay, so that means that when we look at the formula, we'll put 3,000 in for P, and we'll put in 3 for T. 3R. Okay, so there's our formula, 3,000 e to the 3R. This one, R will be 0.01. Okay, this one, R will be 0.02. This one, it's going to be 0.03. That's going to be 0.04, and so on. Okay, so this is good because there's a lot of these. Let's just do this in Excel, so we don't have to write it again. So 3,000 e to the 3R. So let's go punch that into Excel. Dang, now it's. Okay, so here we have the interest rate. And we have 0.01, 0.02, 0.03, 0.04, 0.05, and 0.06. And then the formula, put the equal sign, and then the principal, which is 3,000, times And then remember it's exp of the number of years was 3, so 3 times. And then here we put A23, which will grab that slot there. Okay, so e to the 3 times A23. If I scroll that down, then it's putting a 0.02 in there here, it's putting a 0.03 in for that one, and so on. Okay, so these are the different values. And then I can I can make this, I can adjust it to the right length, and it'll automatically round everything off perfectly. Right there, everything's rounded off good right there. And I was able to do that because they all have the same number of digits. If they had a different number of digits, then it would not work out so well. So these are all the answers to that part. This is just a 0.5 because if I look at it more, like for that, because when you round it off to the nearest cent, this rounds down, and you just have 50 cents. Okay. Okay. So not that. That's too far. Okay. So those are all the answers right there. Let's go back and input those. Okay. And so this is from Excel. Okay. Use exp of, and then I had, what did I have? 3 times. I used the times button. And then I had, these ones was like A23 or something to get all these different values. Okay. So, and then scroll it down to get the different values. So 3,091, 36, 3,185, and 51. I'm just copying it from the other one. You can put a 0 there or leave it off. Okay. So that's from the Excel right there. Okay, let's move on to the next exercise. Number 8. Okay, so this question here is asking which is the best investment. Okay, so you have 2.25% per year compounded monthly, 2.5% per year compounded semi-annually, or 2% per year compounded continuously. Okay, so we want to know which one of those is going to yield the most interest. Okay, that's what they mean by best investment. Which one yields the best interest, the most interest? So it's not giving you the number of years, and it's not giving you the principal. So let's just make up a principal. We'll just say $100, and the number of years, we'll just make that 1. Just kind of really simple thing. So just choose these. You can choose anything really. So by the way, you can choose any numbers for these. You can choose anything here, it doesn't matter. But I'm just choosing those, okay? And so when I make those choices, if I compound monthly, that means that n will be 12. And the formula will be this one. So 100 times 1 plus, and then the rate is 2.25. So that would be 0.02. 1/4 is 0.25, so 25. Okay, so 0.022, oops, 225 over 12 raised to the 12 times 1 raised to the 12th power. So that would be the first one. Second one, the rate is 0.025. 2.5 is 2.5. So move the decimal place over 2 spots. And this will be 100. 1 plus 0.025. Okay, semi-annually means n is 2. That means 2 times a year. So that's a 2. And then this is squared. Okay, and then the last one is this one right here. Here the rate's going to be 0.02. And it's continuously, so that means you use this formula here. And again, the principal is 100, because we chose it to be 100. You could choose something, you could choose different numbers here, and they'll be different. But you have to be consistent. You can't just choose different stuff. But you could make all these 1,000 if you want. So 1,000, 1,000, 1,000. Okay. And then this one, the same thing. One is by far the easiest number to choose here. You can't choose a negative number. It's got to be a number of years. Okay, e to the, and it's going to be RT, so that would be 0.02 times 1. So that's just going to be 0.02 right there, just like that, 0.02. And I'm going to use Excel to figure these out because there's just 3 of these values. Not Excel, GeoGebra. I use GeoGebra to figure this out. Okay, so the first one was 100 times 1 plus 0.0225 over 12, and that's all raised to the 12th power. Okay, so that yields $102.27. And then the next one was 100 times 1 plus 0.025 divided by 2. In GeoGebra, you don't necessarily have to write a times sign, but in Excel you do. Okay, so those are the 3 different values, and it looks like the second one is more than the other ones. The second one is $102.52. The first one is $102.27. This is $102.02. So it looks like the second one is better. Okay, so let's go back. If I can make it back. Okay, so this one turned out to be approximately $102.27. This one turned out to be approximately $102.02. And the middle one turned out to be approximately $102.52. So this one turned out to be, looks like the best. This one looks like the best. So this should be the answer right here. So you just